Now that we know what work is, we're going to apply work with the energy bar charts and figure out how to solve problems that way. I'm going to do two examples, and I would like you to watch both of them so that you can see the two different ways that you could do problems like this. So they're similar, but they do have distinct differences in how you want to approach the problem and then solve. First one tells us that a 20 kilogram cart is at rest at a height of 5 meters. It rolls down the ramp as shown in the diagram. Determine the final velocity of the cart, assuming that 10% of the energy is dissipated by friction. On our diagram, first thing we want to do is label our base level. And then up here would be my height of 5 meters. This will be A at the top and then B at the bottom. So before we list what we're given and what we need to find, let's just draw the energy bar chart. We know that it's got EEL, let's label this EEL, EK, EG, EEL, EK, EG, and I'm going to add another column. And I'm purposely separating it out. And that's because this is called dissipated energy. So this is energy that's going to be leaving the system. It's not disappearing, which is why we still want to show it in the bar charts, but it is leaving the system. So that's why I kind of separate it off. And the other thing I like to do with the dissipated column is it's a visual aid. Just shade it off to show that this is energy that has left the system. Okay, cart is at rest, but it's at a height of 5 meters. So if it's at rest, there's no kinetic energy, there's no spring. All of our energy is gravitational potential energy at A. At B, it's at the base level, so there's no longer any gravitational potential energy. There's still no spring. It is moving, but it's also lost energy. So I'm going to have kinetic energy and dissipated energy. And once again, the only thing that dissipated energy means is that it's energy that has left the system, usually because of friction. You'll notice that the number of bars in A is still equal to the number of bars in B. This will be true anytime you're having energy leaving the system. The only time A and B will not add up is if you start with nothing, work is done to the system, and then you have something. So we'll see a couple of problems like that. But if you have energy and then you're losing energy out of the system, your bar charts are still going to add up. All right, let's list what we're given. And then we'll go ahead and solve. So we know that the mass is 20 kilograms. Height at A is 5 meters. Speed at A is 0 meters per second. And 10% of the energy is dissipated by friction. So that means that the work is going to be equal to negative, and it's negative because it's leaving the system, negative 10% of the energy at A. 10% is the same as saying 0.1. So work is equal to negative 0.1 of the energy at A. Okay, going on to solve. From our bar charts, we still want to list energy at A, but now we're going to say plus work equals energy at B. If you don't do the plus work, you're going to mess up. So believe me when I say you want to do energy at A plus work equals energy at B. Even if work is negative, you still want to keep this as plus work. A side note as to why. Work is equal to the change in energy, so that would be EB minus EA. You could also say that work equals delta E. The only way that you get work equaling delta E is by saying EB minus BA. Rearranged, you get this. I just like this format a little bit better because it lines up nicely with the bar charts. So EA plus work equals EB. Kind of energy at A, we have gravitational potential energy at A plus work equals kinetic energy at B, mg height at A, plus my work, this would be negative 0.1 mg height at A equals 1/2 m VB squared. Now, because I made this substitution here, we knew that work was equal to negative 0.1 EA, so negative 0.1 of EA, which was EGA. So because I made this substitution here, I can cross out my masses. That's not always going to be the case when we're dealing with work. So G height at A minus 0.1 G height at A is 0.9 G height A. Multiply that by 2 equals VB squared. So this would be 1.8 times 9.8 meters per second squared times 5 meters equaling VB squared. This comes out to 88.2 meters squared per second squared. Taking the square root of that, 9.39 keeps on going meters per second. So at the bottom of the ramp, my speed is about equal to 9.4 meters per second. So anytime you see a problem where it's talking about a percentage of energy, you're usually dealing with the percentage of your initial energy at A. Whether or not it's added or taken away depends on the wording of the problem. So if energy is entering the system, this would be positive, but in this case it was leaving, so we had to make that negative. Okay, one more example, it's a little bit different. Tells us a 25-gram bullet traveling at 350 meters per second strikes the block of wood, which exerts on average 50,000 newtons of force opposing the motion of the bullet. How far into the block does the bullet come to rest? For this one, I'm going to make this my base level. It just makes sense. That way the bullet never has any height. Listing what we know. Mass is 25 grams, so that would be equal to 0.025 kilograms. My velocity, this is A, this is B. Velocity at A equals 350 meters per second. Velocity at B comes to rest would be 0 meters per second. And there's a force opposing the motion equal to 50,000 newtons. And we are looking for how far the bullet comes to rest, so we're looking for D, the distance that the bullet goes into the block. So for my energy bar charts, EEL, EK, EG, EEL, EK, EG, and we want to add in that other dissipated energy column. So in this case, there's no spring, it is moving, there's no height. So we start with only kinetic energy. It comes to rest, so there's no movement, there's no height, there's no spring. All of the energy here was dissipated. Energy at A plus work equals energy at B. This becomes a little bit easier because your energy at B is 0. Kinetic energy at A plus work equals 0. 1/2 m VA squared equals, I'm just going to bring this over to the other side, negative work. In this case, we need to use the formula for work, FD cosine phi. Nothing cancels out here because mass is only in the kinetic energy equation, but we know mass, we know VA, we know force. Phi we're going to find right now. The only thing left to find is distance. So remember, phi is the angle between the distance that the object moves. So it's moving to the right, but the force is opposing. Force goes to the left. So that means that phi equals 180 degrees. isolating to solve for D, we get 1/2 mVA squared over negative F cosine phi equals D. 1/2 of 0.025 kilograms times 350 meters per second squared over negative 50,000 newtons times the cosine of 180 degrees equals D. So because this cosine of 180 is a -1 and this was negative just from the algebra, this will come out to be a positive number. That makes sense because the bullet is moving to the right. Putting all of these numbers in, we should get, if you put it in your calculator right, 0.0306 keeps on going meters for the distance. So it comes to rest about 3 centimeters into the block of wood. So distance is about 0.031 meters. So 2 types of energy problems when we're dealing with work. I don't think you have many more variations of either of these, but it is useful to know how to do both. We'll do some practice tomorrow in class, and hopefully you don't find these too difficult.